Today, I'm going to be talking about algorithms and certificates for Boolean CSP Refutation. I'm Peter, and this is joint work with Guruswami and Pravesh Kothari here at Carnegie Mellon University. So I'd like to start off by talking a bit about 3-SAT. As we know, 3-SAT is an NP-complete problem, and moreover, it's hard to approximate. That is, it's NP hard to even find an assignment to the variables that satisfies more than 7/8 plus epsilon fraction of the constraints. Now remember that a uniformly random assignment to the variables will satisfy 7/8 fraction of the constraints in expectation. So essentially, it's NP hard to do anything even a little bit better than that. If we're willing to assume the exponential time hypothesis, that is that 3-SAT requires exponential time, then we get a more interesting picture for hardest approximation. That is, we'll get a trade-off between the time required to get a good approximate solution and the number of constraints in the instance. So I can draw this on this graph, where on the x-axis, I have the number of constraints, and on the y-axis, I have the runtime of the algorithm. So result due to Impagliazzo and Berturi shows that even beating 7/8 plus epsilon requires exponential time when the instance has order n constraints. But on the other hand, Aurora, Carter, and Karpinski showed that there's a polynomial time approximation scheme when the instance is fully dense, that is, it has order n cubed constraints. This hardness line was later extended by Fotakis, Lampish, and Pashos all the way up to n squared constraints, and they additionally showed a sub-exponential time approximation algorithm where the runtime of the algorithm trades off between the number of constraints required in the instance in order to get a good approximation. So we would nonetheless like to have good algorithms for KSAT in spite of this worst case hardness picture. So one way to circumvent all this worst case hardness is instead to try to solve random KSAT instances. This unfortunately has a small problem that a random KSAT instance phi with order n constraints is not satisfiable with high probability. So if our definition of solving means that we just want our answer to be correct with high probability over the instance, then this is trivial to achieve. We can simply always output unsatisfiable, and this will indeed be the correct answer with high probability. So one way to recover a non-trivial task in this average case setting is to instead ask that our algorithm certifies unsatisfiability. So this task is going to be the focus of this talk. What do I mean by certifying unsatisfiability? Well, I can formalize this by defining what's known as a refutation algorithm. So this is an algorithm A that takes as input an instance phi and outputs either unsatisfiable or I don't know. And we want this algorithm to satisfy two guarantees. The first is correctness, that is that A of phi, if it outputs unsatisfiable, then phi must indeed be unsatisfiable. That is, this is a zero error condition, so we can never make a mistake here. If the instance is satisfiable, then we can never be outputting unsatisfied. On the other hand, there is an algorithm that trivially satisfies condition 1. The algorithm A could just be outputting I don't know always. So the condition 2 says that A must be doing something somewhat useful, that is, A must be outputting unsatisfiable with high probability when phi is a random instance. And if A satisfies these two conditions, I'll say that A is refuting random KSAT instances with high probability. So there's two things I would like to point out here. The first is if we kind of view this from an algorithmic design standpoint, if we're deciding whether to output unsatisfiable or I don't know on the instance phi, well, we have to really figure out that phi is unsatisfiable when we choose to output unsatisfiable, because we cannot make a mistake. So we have to really know that phi is unsatisfiable when we're outputting unsat. On the other hand, from a complexity viewpoint, if we have such an algorithm A, and it outputs unsatisfiable on an instance phi, then this is a certificate that phi is unsatisfiable. That is, we've proven that this is the case. So when I say certifying unsatisfiability, this refutation algorithm A is the certificate itself. So refuting random KSAT is a pretty well-studied problem at this point, and we now understand this pretty well. So there's this theorem due to Raghavendra Rao and Shram, which shows that for every parameter L, there's an n to the order L time algorithm to refute random KSAT instances, provided they have at least L times n over L to the k over 2 constraints. And I should mention that for this talk, I'm going to pretend that log n is constant, so I'm going to suppress log factors throughout all theorems. So I like to draw your attention to two choices of the parameter L. The first is when L is constant. This is a polynomial time algorithm, and this says that we need n to the k over 2 constraints in order to refute. And the other choice of L is when L is n to the delta, then this algorithm is running in 2 to the n to the delta time, and it says that we need this number of constraints in order to refute. An important point here is that as delta approaches 1, number of constraints we need approaches order n, which is the unsatisfiability threshold for random k-set. So as we get to fully exponential time, we need basically optimal number of constraints. I can draw this on a picture here, where in the background I put the worst case hardness picture. And at end of the k/2, we have from RRS, we have this refutation algorithm, and we also get this sub-exponential time trade-off going down all the way to the order n constraints. On the other hand, there is a matching lower bound down here. This work due to Kothari, Mori, O'Donnell, and Thittmer shows that n to the order L time SDP-based algorithms need this number of constraints in order to refute. And by SDP-based algorithms, I simply mean degree order L sum of squares. And if I draw this on this picture, we just get this matching lower bound here. So refuting random k-set instances in some sense is solved. We have this type picture, which is when m is above this L times n over L to the k/2 threshold, we can refute n to the order L time, and otherwise we cannot, assuming our algorithm is a sum of squares based algorithm, which pretty much every algorithm designed for this task is. So what is our work going to be about? Well, I could draw this picture where on the left I have fully random instances, which have like the most amount of randomness possible. And on the right, I have worst case instances, which have almost no randomness whatsoever. And we can ask, what happens in the middle? Like what happens if we have an instance which has some amount of randomness, but isn't quite as random as a fully random instance? And so that's going to be the focus of our work. So to do this, I have to define what a smoothed k-set instance is. And a smooth instance is formed as follows. We first just start with an arbitrary instance, okay? And we will go through each literal negation and flip it with probability of, say, p equals 1 over 100 independently. And p can be any just small constant. So that's all we're going to do. And we could, for example, flip some of the literal negations here because p is kind of small. Only one negation got flipped, the one on x sub 12. And this produces our smooth instance. So this is the distribution over instances we will consider. So the distribution is parameterized by this underlying phi. To mention that the scopes of phi, which are defined by this hypergraph H, where the hyper edges just tell you which variables are in which clauses. So for example, the first hyper edge is 1, 2, and 6 because x1, x2, and 6 appear in the first clause. This hypergraph is arbitrary because the instance was arbitrary, and the only thing we did was flip the negation pattern. Moreover, the literal negations are also almost arbitrary. We've just applied a small perturbation to them. So you can think of the instance phi as being specified by these two things, the hypergraph and the negations. And the only thing we've messed with are the negations, and we haven't even modified them by that much because p is kind of a small constant. I should point out that when p is a half, these instances are called semi-random. When p is a half, then this means that the literal negations will become uniformly random bits. And a semi-random instance, therefore, is just like a random instance, but this H is worst case. And if we were to draw this on this random versus worst case picture, semi-random has less randomness than random, and smooth has even less randomness than semi-random. So what's known for refuting semi-random instances? Well, we still have this lower bound. It still applies. But other than that, there's just this theorem due to Abascal, Guruswami, and Kothari, which show a polynomial time algorithm to refute semi-random instances at end of the k/2 constraint. So that's on the picture. Might notice that this is the L equals order 1 case. It also only applies to semi-random. It doesn't go all the way to smooth. And in particular, there's also this no sub-exponential time trade-off here. The smooth picture, even less is known. We just don't really know anything. There's one algorithm known due to Feige that achieves some weaker guarantees. But other than that, we don't really have anything. So our first result is we prove essentially the full picture for smooth k-set. That is, we show that for every L, there's an n to the order L time algorithm to refute smooth k-set instances with this number of constraints. And this is the same trade-off as in RRS, the theorem for random k-set. So the only thing that's really different in our theorems is we've swapped the word random out with the word smooth. But remember, this is a pretty substantial upgrade because smooth instances are almost worst case. They have far less randomness than a fully random instances. So on this picture, our theorem 1 shows this refutation algorithm and also the sub-exponential time trade-off. So Our theorem also has some interesting consequences for the landscape of K-SAT instances. So our theorem says that smooth instances, provided we're above this threshold, are pretty easy to refute. And in particular, this tells us that if an instance is hard to refute, then the hardness must only come from the literal negations. Because remember, this hypergraph was fixed. It was worst case in a smooth instance. Moreover, the hardness coming from the literal negations must be pretty brittle, because the small perturbation applied by the smoothing process is killing the hardness. It's making it easy to refute. And we can draw this kind of as a picture here, where I have this picture where I put a dot for each K-SAT instance phi. I'm coloring the dot green if the instance is easy to refute, and red if it's hard to refute in some informal sense. And we know the picture for random looks like this. That is, if we look at all instances, most of them are pretty easy to refute, because this is what RS shows, that they can refute with high probability. Our theorem for semi-random says that if we zoom in really close on one instance, and we look at all instances with the same hypergraph but uniformly random negations, locally, this again looks pretty easy. Most instances are easy. And the picture for smooth says if we zoom in even closer and look at the same H and only a small perturbation to the literal negations, still most instances locally look easy. And in particular, there are no clusters of instances which are all very hard to refute. And this could have been the case a priori, but we've proven that this does not happen. So that's all I really want to say about algorithms. The title of our talk is Algorithms and Certificates. And so far I've just talked about algorithms. So I think now it's time to move on and say a few words about the certificates. So recall the picture for random 3-set, where we have this refutation algorithm at n to the 1.5 constraints. And below that, we have the sub-exponential time trade. Now there's this interesting result due to Feige, Kim, and Ofek, who show that for random 3-set instances, there is a refutation witness at n to the 1.4 constraints. And what I mean by this formally is that the refutation algorithm at non-deterministic polynomial time can refute at n to the 1.4 constraints. And n to the 1.4 is lower than n to the 1.5, the threshold we need to refute if the algorithm is deterministic polynomial time. So what's going on here? Well, they construct this witness using even covers in this hypergraph page. And an even cover is just a collection of distinct hyperedges such that the symmetric difference over the hyperedges is the empty set. Equivalently, every vertex is appearing in an even number of these hyperedges. So for example, this is an even cover because, as you can check, each vertex is appearing in an even number, in fact, exactly 2 of the hyperedges. In light of this connection to even covers, Feige came up with the following conjecture, that every K uniform hypergraph with at least m about L times n over L to the K over 2 hyperedges must have an even cover of length order L. And the length of the even cover is simply the number of hyperedges in the even cover, which is this parameter R up here. So I haven't said what a K uniform hypergraph is, but it's just a hypergraph where every hyperedge has size exactly K. That is, it's a collection of subsets of the vertices where each subset has size exactly. And there's a connection known that Feige's conjecture combined with a refutation algorithm for smoothed K-SAT will imply the existence of these FKO certificates for smooth K-SAT as well. So the heart of the matter is in this conjecture. So let's talk about it a bit more. So when K equals 2, a K uniform hypergraph is just a graph, and an even cover in a graph corresponds to a cycle. So this is actually the well-known Moore bound, which says that every graph with 2 ND edges has to have a cycle of length about log n. Feige's conjecture has also been proven when K is even and L is constant, and also was later extended for all K when L is constant. So what do we do here? Well, this is Feige's conjecture, and now it's our theorem. So we prove this conjecture. And then we just combine it with our refutation algorithm for smooth instances, and we get this. We show the existence of these FKO certificates for smooth instances as well. And this leads us to our theorem 3, which shows that for smooth 3-set instances, there are refutation witnesses at n to the 1.4 constraints. And for K larger than 3, we get a different threshold. We get something that tends to about n to the K over 2 minus 0.5, but This doesn't really matter. The important point is that we're beating n to the k over 2 by a polynomial factor. And remember, n to the k over 2 is the threshold we needed in order to be able to refute with efficient deterministic algorithm. So just to summarize, for first theorem, we provide the refutation algorithm for smooth k-sat. This upgrades RRS by extending their result from random instances to smooth, and it upgrades AGK by extending their result for semi-random to all L and also getting it for smooth instances, not just semi-random. I should mention our theorem also holds for any Boolean KCSP, not just KSAT. In fact, pretty much all our theorems would extend to this case as well. The second theorem, we prove Feige's conjecture. And in our third theorem, we combine theorems 1 and 2 to show that for smooth 3-sat, there are refutation witnesses at n to the 1.4 constraints. And this is an upgrade on the result of FKO because we've again swapped the word random 3-sat for smooth 3-sat. And so in this sense, we're proving that the smooth matches random. That is, the thresholds for refuting smooth instances are the same as those for random. So now I would like to just say a few words about the proofs. So first, I'm going to discuss refutation for random 4 XOR instances. This result is covered by RRS because it's for random instances, but the proof I'll present is due to Wine, El Alawi, and Moore. I should mention that K XOR is really the only CSP you need to refute. Now, once you refute K XOR, you can refute any other CSP. And here I just want to give a flavor for a proof, even if I'm going to go over this a bit fast. And I chose 4 XOR because 4 is an even number, and the case of odd K is a lot more complicated. Then I will talk a bit about Feige's conjecture for 4 uniform hypergraphs. And here I just want to explain the high-level idea. So let's move on to 4 XOR. And here I'm going to have to introduce some notation. So I'm going to encode the 4 XOR instance first by the hypergraph H, and then the right-hand side's B sub C's. These are plus minus 1 random variables. So the constraints will then just be take the product of all the variables in C for a hyperedge C and want that to be equal to B sub C, where B sub C is this plus minus 1. Now remember, I'm using products because I'm in plus minus 1 notation and X is a plus minus 1 vector. As an example, we could have the constraint x1, x4, x8, x12 is equal to 1. This is saying C is 1, 4, 8, 12, and B sub C is 1. And here's another example. So how do we analyze this? Well, we first observe that the fraction of constraints satisfied by assignment x can be written as a half plus a half times f of x, where f of x is the following bias polynomial. It's the average over the constraints of this inner term, b sub c times the product of I and c of x of I, which you should notice is plus 1 when the constraint is satisfied and minus 1 when it is unsatisfied. So our goal now is to just show that f of x is at most, say, 1 over 100 for every x, provided that m is at least n squared over l. And if we can do this, then the number of constraints satisfied by any x can be at most half plus some small constant, and we'll have succeeded in refuting the random 4 XOR instance. So that's our goal. How do we achieve it? Well, what we do is we introduce this matrix A. It's going to be indexed by subsets S and T of size L. And we first define A sub C to be a matrix where the S-teeth entry is 1 if the symmetric difference with S and T is equal to C. And then we just set A to be the sum over the constraints of B sub C times A sub C. And let me interpret the symmetric difference condition a little bit. So if C is size 4, then we can break it up into 2 subsets of size 2. And the only way for the symmetric difference of S and T to be C is if S contains half of the clause C along with L minus 2 other variables, and T contains the other half of C along with the same L minus 2 variables. And then you can see when we take the symmetric difference, the orange set will cancel and be left with just the blue and the purple, which is equal to C. Okay, so let's just finish the analysis here. There's a pretty simple fact that up to some scaling factors, f of x can be written as a quadratic form on A, where we just take this vector z, which is achieved by lifting the assignment x to sets of size exactly L. So remember, x is plus minus 1 and z is plus minus 1 to the n choose L, and that's why I'm taking products. And then if the spectral norm of A is not too large, we can upper bound the z transpose az, the quadratic form, using the spectral norm, and we get this inequality. And rearranging, massaging some things, we see that when m is about n squared over L, this will certify an upper bound of some small constant on f of x. So the real thing to do here is to show this high probability upper bound on the spectral norm of A. And this is actually not that hard when the hypergraph is random, using just some off-the-shelf matrix Bernstein concentration interval. So at this point, you might feel a little confused because I promised a refutation algorithm. I have yet to tell you what the algorithm is. So what's the algorithm here? Well, it's pretty simple to actually read off from this slide. Given the 4XOR instance, we just construct this matrix A, compute its spectral norm, rearrange these terms in this inequality, and we'll get an upper bound on f of x that will be true for any 4XOR instance. And then the proof on this slide is simply saying that if we have a random 4XOR instance with high probability, we'll certify a good upper bound on f of x. So that's really all I wanted to say for 4XOR. Now I'm going to move on to Feige's conjecture. So in Feige's conjecture, we start with a 4 uniform hypergraph with n squared over L hyperedges. And we want to show that there is no length order L even covered. So we're going to assume that, we want to show that there is a length order L even covered. So we're going to assume that there is no such even covered. So what we do is we set f of x to be the same polynomial as before, but now the b sub c's are up to us to choose because there's no 4XOR instance. So we'll set b sub c to be 1 for every c. Then what we do is we show that our refutation algorithm will in fact certify that f of x is at most 0.01 for every x. And you should think, hang on a minute, this is obviously false because the b sub c's are all 1, which means that if I set x sub I to be 1 for every I, then this product in here will be 1. I sum over all constraints, I get m, I divide by m, so the average is 1. So f of the all ones thing is equal to 1. So this is a contradiction, which then implies that H must have a length order L even. The key observation here, the key idea, is that if there is no even cover, then we can refute f of x for any b sub c's, and this is just an insanely strong condition. There's no way this is true. So that's how we get our contradiction. And this is kind of, I think it's an unusual proof, and I think we really required this refutation perspective in order to see it. So yeah, I think there's a kind of interesting connection here between even covers and refutation that we are exploiting in order to prove this conjecture. So just to summarize, we have a few results. Our first theorem, we show that this algorithm for refuting smooth K-sat, and this additionally implies that this hardness of refuting K-sat instances is really coming from the literal negations. And this hardness is brittle and that a small perturbation is killing the hardness. We then had this picture showing that, like, as we zoomed in really close on one instance, all the instances around it still looked kind of easy to refute, so we did not have clusters of hard instances. We then showed theorem 2, where we proved Feige's conjecture, and then combining with our refutation algorithm for smooth K-sat, we showed the existence of refutation witnesses for smooth K-sat instances below this end of the K/2 threshold. Takeaway from all the results is that smooth instances are no harder to refute than random ones. We can refute them at the same threshold that we can for random. And that's encapsulated by this picture here, where our paper essentially fills out this entire picture and makes it exactly the same as the picture that was known a priori for random instances. And that's all I have time to say. Thanks for watching.